So this is our third tech talk for the fall of 2014 statistics. And we're going to talk about a few things. We're going to talk about how to calculate statistics of group data. We'll also talk about how to use the graphing calculator to compute probabilities using counting techniques. All right, so first of all, in the graphing calculator in the statistics menu, I've got two columns. In the first column, I've got values. These values could be midpoints of intervals. And then in the second column, I would have frequencies for each of those values. So for example, if you have a frequency distribution in which you have intervals in one column and frequencies in the second column, well, in the first column here, you would want the midpoints for those intervals. Okay? So if you want to play along, you can copy these numbers if you want, or any other numbers just to play along. Okay. So first column, we've got values. Second column, we've got frequencies. L1 is the first list, and L2 is the second list. All right, so I'm going to quit. Go back to the home screen. Go back into the statistics menu. Right arrow over to the calculate submenu. And select that first option, one variable statistics. Now, if I were not to select any other or any list or anything, by default, the calculator will assume that you just mean for it to calculate the statistics for the data in list L1. Now, if we wanted to compute the statistics for list L2, then we can just select the list L2. And it'll go ahead and calculate the statistics for the data in list L2. But what we want here is we want it to calculate the statistics for the group data in list L1 values and L2 frequencies. So to do that, we'll go into statistics, calculate one variable statistics, and we're going to put L1, comma, L2. Everybody see what I did there? L1, comma, L2. This tells the computer that the values are in list L1 and that the frequencies are in list L2. Now, to get list L1 and L2, just look, you see your keys for 1, 2, 3, 4, 5, 6. You hit the second button to access L1, L2, L3, L4, L5, L6. If you don't remember that, you could always go into your list menu and then select any of those lists here. Okay. Anyway, and so after you put in one variable statistics, L1, comma, L2, go ahead and hit enter. X bar is going to be the mean. Sigma X is going to be the sum of the values, as in sum of the values with the frequencies applied. Skip on down to S sub X. This guy right here, the S sub X, that's going to be the standard deviation for that group data. Okay? The N, of course, that's the total number of frequencies. That's the total number of individuals in that set. By the way, here's your 5-number summary down here. Min, Q1, median, Q3, and maximum. Now, I'm going to quit out of this, or clear. Now, if you cleared that and you forgot, what was S sub X again? Well, you see the variables button right here? Click on variables button, and then scroll down to option 5 where it says statistics. And then you could pick out whatever statistic that you wanted it to. For example, S sub X, which is 3. So if you wanted to know the standard deviation for that computation that you just did, there it is. If you want the variance, then all you need to do is square it. So hit the square button. And so that sample variance will be what you see there. Just standard deviation squared. Okay? All right. Any questions so far? Does that help with your computations for group standard deviation? Now, you're probably thinking, boy, I wish that I would have known this a while back, huh? But I'm also going to tell you that if you just go onto Google and just enter, calculate standard deviation of group data using my TI-84, there's resources out there. There's people who've already posted how to do that out there. For example. All right. I'm going to quit out of there. Clear. Now, regarding counting techniques, we talked about permutations, and in particular the factorial. To do 10 factorial, you input 10, and then go in your math menu, probability, factorial is the fourth option, and hit enter. So there's 10 factorial. To do the Mississippi problem, that was 11 factorial. Excuse me, math menu, probability, option 4. So there's 11 factorial. Divide that by, and in parentheses, you're going to do 4 factorial times 4. And you don't need to put a time sign there, because when you put the 4 after the factorial symbol, the calculator automatically knows that it's multiplication. So 4 factorial, again, and then 2 factorial, which is 2, by the way. And there was your answer there. Regarding the lottery, the probability of winning that lottery, where you had to choose 6 numbers from 49, the probability is 1 divided by 49 choose 6. So you want to do 49 choose 6. So you do 49 math NCR, which is the third option in the probability menu, and then 6. So there's your 49 choose 6 in parentheses. And so it's a very small number. Don't ask me to write it as a fraction, but there it is as a decimal. All right, let's do a couple more problems here. Let's play poker. Want to play some poker? So I'm going to deal you 5 cards. All right, do you know what a full house is? Full house is what? 3 of a kind and 2 of a kind, right? So a triple and a pair, right? So probability of a full house. Well, we're going to count the number of ways of getting a full house, huh? So we're going to get a triple. Let's count the number of ways that we get a triple, right? How many values are there? 13? So there's 13 ways of choosing a value. Once we choose a value, there's 4 cards for each value. So maybe it's a 2. There's 4 2. How many ways can we choose 3 2s from 4? And the answer is 4 choose 3. Because order doesn't matter, huh? So that's 4 NCR 3. And then we're going to choose a value for the double. And there's going to be 12 ways of choosing that value. It's going to be a different value than for the triple. And there's 4 cards for that value. There's 4 choose 2 ways of choosing the 2 cards from the 4th for that double. So the number of ways of choosing a full house, here they are. It's 13 times 4 choose 3 times 12 times 4 choose 2. And then divide that by the total number of possible 5-card hands from the deck. and that's going to be 52, choose 5. Okay, everybody understand the setup there? Remember, calculate theoretical probability. You're going to count the number of ways that your event could happen, divided by the total number of possible outcomes. So in the numerator, you got all the possible full houses that are out there that are possible for you to be dealt, divided by 52, choose 5, which is all the possible 5-card hands. Now, how to calculate this, you have 13 times, and in parentheses, I'm going to do 4, and then math, NCR 3, and then times 12 times, and in parentheses, I'm going to do 4, math, NCR 2. And then I'm going to divide that by, and in parentheses, I'm going to do 52, math, probability, NCR 5. Enter. And that's approximately 0.00144. So that's the probability of being dealt a full house. So that means out of every 1,000 poker hands that you could expect to be dealt about 1 or 2 full houses. That's how you can interpret that probability. Everybody understand? Okay, let's calculate the probability of getting some other hand. How about a royal flush? Probability of getting a royal flush. Now, how many ways can you get? By the way, what is a royal flush? Oh, hold on. Royal flush. A royal flush is what? Okay, so we're talking about aces high, and you are dealt a 10, jack, queen, king, ace of the same suit, huh? It's a flush because they're all 5 cards of the same suit, and it's a straight, but it's a royal straight because of the 10, jack, queen, king, ace. Now, if you're playing aces low, then the royal flush would be a 9, 10, jack, queen, king. 9, 10, jack, queen, king. Anyway, okay. All right. So how many royal flushes are there in the deck? 4. Exactly. There's only 4 ways of being dealt a royal flush. 1 for each suit. Right? There's a royal flush for, spades and clubs, diamonds and hearts. Huh. And divided by 52, choose 5. So let's calculate that. 4 divided by, and in parentheses we have 52, math, NCR 5. So we're talking about 1.5 times 10 to the negative 6 power. So that means about out of every million poker hands, you could expect to get maybe 1 or 2 royal flushes. And so it's more likely for you to be dealt a royal flush than to win the lottery by about 100 times. So those of you who like to gamble, so you're probably giving your money to a good cause, like supporting your schools and stuff. But it's not very likely that. But hey, it's hope. It's entertainment. If and like I tell my wife, I said, look, I know too much about gambling. I don't gamble. But so if you choose to spend money, that's actually going to be my money because she doesn't work. But just understand when you purchase a lottery ticket, you shouldn't be thinking about it as a retirement plan. Think of it as entertainment.
Couldn't you take her to Vegas and take those same statistics and probabilities of
See, I suck at card counting. I've tried to card. I'm not a card counter. And I don't like casinos. It just kind of gives me the creeps. Whenever I've gone to casinos, I go to the gift shop, and then I go to the buffet, and that's where you could find me. And then come collect me on your way out, because I'm going to be on my third tray of food until I'm bulging. And then I might be passed out on some bench somewhere. And then just collect me on the way out. So anyway, I wanted to do one last problem with you, which I think is interesting, and this will close out chapter 4. And this is going to be the so-called birthday problem. So I don't think we're going to start chapter 5 tonight, and that's okay. We'll start it on Monday. The birthday problem. No, Wednesday. Remember, I sent out an email yesterday, and it said Thursday, and then I had retracted that. It changed it because, of course, we don't meet on Thursday. It's Wednesday. I know I had said Monday, but I changed it because I was sick last Monday night. I'll talk, before we part ways tonight, I'm going to talk about the test a little bit. Anyway, let's talk about the birthday problem. So how it goes like this. You suppose that you have a room containing n number of people. Now, what is the probability if I could spell it, probability that at least 2 people sorry, I can't spell tonight. 2 people have the same birthday. Have same birthday. So now what I mean by that is maybe 2 people have the same birthday, maybe 2 people have the same birthday and another 2 people have some other birthday in common, maybe 3 people have the same birthday. And as it turned out, when I did this problem yesterday with my afternoon class, that I had 3 pairs of students sharing birthdays. And that's never happened with 11 years of teaching here, whenever I've done this problem. So that was a very unique. So we'll see what happens here with us. All right, so let's count the number of people that we have in the room here tonight. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So there's 17 people here. So we're going to temporarily replace n by 17 for our problem here. So there's 17 of us in the room. What's the probability that at least 2 of us have the same birthday? And the reason that we want to know this is that, I talked a little bit about coincidences, what we think is a coincidence, right? You bump into an old friend in the airport. Hey, what are the chances that you and I would meet here at Chicago O'Hare? Well, actually, you shouldn't be too surprised, because if you travel a lot and he or she travels a lot, it's bound to happen sooner or later. Or, you flip a coin 10 times and you get 10 tails in a row. Do you think that's a coincidence? Maybe, but you're just as likely to get heads, tails, tails, heads, heads, tails, heads, tails, heads, tails, as 10 tails in a row. So what you might think is a coincidence maybe is not so unlikely after all, huh? Okay, so in order for us to calculate the probability that at least 2 people share the same birthday, we're first going to calculate the probability that no 2 people have the same birthday. So that means as we go around the room I'm going to have birthday different from yours. That's different from yours. That's different from yours. So there's 365 ways that I could have a birthday. And then there's 364 ways that Carlos could have birthdays separate from mine. And there's 363 ways that you could have a birthday separate from the two of ours. And there are 362 ways that you could have a birthday separate from ours. And on down the line, ... all the way down to 360 or 349. So if you were to count out these numbers, there would actually be 17 integers there. Divided by the total number of ways that 17 of us could have birthdays. So 365 raised to the 17th power. Now, and then we're going to subtract that from 1. Now, let me redo this. 1 minus. In the numerator, actually that's a permutation of 365 taken 17 at a time. Divided by 365 raised to the 17th power. And in general, if you have n people in the room, the probability that at least 2 people share the same birthday would be 1 minus 365 permutations taken n at a time over 365 raised to the nth power. But let's go ahead and do it for the 17 people that we've got in this room. On the graphing calculator here, we've got 1 minus, and in the parentheses, open parentheses, I'm going to do 365, math, probability, NPR, which is option 2, 17, close parentheses, divided by 365 raised to the 17th power. Enter. And the answer is about 0.315. So slightly less than a 1/3 chance that at least 2 of us have the same birthday. So let's go around the room and see if any 2 of us actually do share the same birthday. So I'm going to call off my birthday, and we'll go along and do the same thing and see if any 2 of us have the same birthday. So I was born on February 21st. Carlos?
April 8th.
April 8th.
May 12th.
May 12th.
June 1st.
June 1st.
November 7th.
November 7th. January 3rd. October 28th.
October 13th.
October 13th. Say again.
August 24th.
24th. August 24th.
July 31st.
July 31st. August 27th.
March 13th.
March 13th.
November 14th.
November 14th.
November 19th.
November 19th. March 20th.
February 9th.
February 9th. So are there any matches? Oh, what was yours? February 26th. Almost a leap year, baby. Almost. But no, are there any matches? Okay, all right. So there was a 68.5% chance that there wouldn't be any matches. But it wouldn't have been unusual if at least 2 of us did have a matching birthday, huh? Remember, if the probability of something happening is 5% or less, then it would be unusual, huh? Yeah, you see what I'm saying here? Now, let me go ahead and take this further. We've got a few more minutes left in class. Go on your graphing calculator and go into your equation editor. Do you see your y equals menu here? Go ahead and oh, by the way, go into your stats plot and turn off your first stats plot if you've got it on. Go ahead and turn that off. All right, so go in your equation editor, y equals, and go 1 minus, and in open parentheses, we're going to take 365, math, probability, NPR, which is option 2, and then x, close parentheses, and then divide that by 365 raised to the x power, where x is the number of people in the room. And now we're going to go into the window, and we're going to let x go from 0 to, say, 400, with maybe divisions of 50, x scale of 50. And on the y-axis, we're going to have probability. That goes from 0 to 1. So we can have y minimum of 0, y max of 1, maybe a tick mark every 0.2. And let's see if we did this right. Maybe not. Check the window. That looks right. Let's check our formula here. 1 minus Interesting. Let's see what's going on here. This is embarrassing. I thought it was going to work out better than this. Interesting. Well, I'll just leave it at that. What I'm looking for is if you were to plot the graph of this probability function, and on the horizontal, you've got the number of people in the room, and on the vertical, you've got the probability of having at least 2 people having the same birthday. Now, when you get up to 365, actually 366, there's going to be a probability of 1 that you will have at least 2 people with the same birthday. But the way the graph goes like this, and it's a shame I didn't pull it up this time, and it's going to look something like that. In fact, it's going to rise even more quickly. But actually, hold on, let me back this up here. It's going to actually rise pretty dramatically like that and level off like that. So by the time you got something like 40 people in a room, the probability is about a half that at least 2 people share the same birthday. And then it levels off from there. So if you've got, say, a group of 100, like, for example, in the Senate, there's 100 senators. There's a very good chance, like a 70-something% chance, that at least 2 of them to share the same birthday. But if you've got the House of Representatives with 435 of them, then there's a probability of 1 that at least 2 of them have the same birthday, because there's more than 365. Now, what assumptions are we making here with this calculation?
That's not a leap year.
No leap year. And what's the other assumption, do you think? It has to do with independence. There aren't any twins, and that everybody is equally likely to be born on any given day of the year. And do you think that really is true? Did you know right now there's kind of a population boom right now, a baby boom in the local hospitals? So if you think back, what was going on 9 months ago? Polar vortex, right. And people were hunkering down and having a good time. So here we are 9 months later, and a lot of babies are being born. So there are times of the year when babies are more likely to be born than others. But we in statistics like to make certain assumptions, like, for example, independence, which are really oversimplifications of reality. But in order to make the calculations at least reasonable, it's not too much of a stretch to assume independence, though. All right, so any questions about what we just talked about regarding probability calculations and numerical counting techniques or anything? All right, when we come back on Monday, we're going to talk about the material in chapter 5.